So, hello student. So, myself is Professor Samudra Roy and our course is Foundation of Classical Electrodynamics and I am from Department of Physics, IIT Kharagpur. So, before starting the course, I would like to say the name of the textbooks that the student should go through, and the first three you can see 1, 2, 3 it is written in the screen. Introduction to the Electrodynamics by Griffiths. This is a very popular book among the students. So, you can go through with these books, and then you can also read Electromagnetism by Pollock and Stump, and then another very nice book that you can go through is Modern Electrodynamics by Zangwill. Apart from these three books, textbooks, we have two reference. I like to suggest two reference book. One is Classical Electrodynamics by J.D. Jackson, and another is Feynman's Lecture volume 2. So, these two books you can also read as a reference reading. In today's class, we will mainly discuss about the vector analysis and scalar and vector fields and vector identities, which should be in module 1, and that is mathematical preliminaries. So, in order to understand electrodynamics, you need to learn in the initial stage few mathematical preliminaries, which are very important for this course, because later on we will do many problems, many treatments based on the electromagnetic theory in electrostatic and magnetostatic, and all these mathematical preliminaries will help you to understand the process that we going through step by step. Okay, so with that note, let me start in today's class number 1. Okay. So, as I mentioned in the first class, we will mainly discuss about the properties of the vectors, and let us start the topic vector. Analysis. So, what is vector first, and that we need to know, but before that, what is scalar, that we need to understand. And scalar is nothing but a quantity that has only magnitude. So, a quantity which is only having a magnitude is called the scalar quantity. We all know that. On the other hand, vector, a quantity that should have both magnitude and another very important thing, and that is direction. Magnitude and direction. So, that means if I consider only a length of certain quantity here, if I want to understand this graphically, then this amount of length, only the length, is a scalar quantity. However, it is not only length, you can mass and other quantities are also under scalar quantity, but if I want to understand graphically or pictorially, then a line is there, and if I only measure the length, then that should be a scalar quantity. On the other hand, if I have a line and not only the length, but the direction if I also measure, then that should be a vector quantity. So, here we are just concerned about the magnitude. Here we also want to understand what is the direction. Since the directions are important, so in vector quantity, when we define a vector quantity, we should have a coordinate system, because if you fix a coordinate system, then it will be easier for us to define a vector. And then suppose this is a coordinate system, let us consider this is a Cartesian coordinate system having only x, y, z, and I am having a vector called say r vector, big R vector, and I always put this vector in this form like a straight line and showing that it is having a length, not only that it is having a distance also, and it can change, this distance can change. There will be infinite amount of change one can make as far as the distance is concerned, as far as the direction is concerned. So, the direction is changing here. So, I am having a vector here, the direction is changing, this is a vector, also this is a vector. So, vector is a quantity that is containing the magnitude as well as the direction, and I can represent this vector to some coordinate system. I have a fixed axis, and on that axis I can just put this quantity vector, which we call vector, like this way. We will discuss later in this all these aspects of vector. But before that, let us understand the next thing, which is called the field. What is field? A function that satisfies a particular quantity everywhere in a region. So, I can have a region, and in this region I can define a function, and this function can take whatever the value it possible. I can show you some example, then things will be clear. So, field is eventually a function, and that function can take different value in a given region. At this moment, let us understand the field in this way. Now, there are two kinds of field possible. One is scalar field, and another is vector field. So, what is scalar field? A function of a space, say, whose value at each point is a scalar quantity. So, I can define a field which is a function that can take different values in a given region, and now I am specifying that a function in a space, that is a function that depends on the different points in the space, and the value of that particular function should be a scalar quantity. So, the example should be the temperature in the very famous example temperature in a space. So, how it is become a scalar field? Let us try to understand quickly. So, I can have a coordinate system here x, y and z, and in this coordinate system this is a space I am defining, and different points I can define the temperature. So, for example, at some point here my temperature T I can define, and this is a value of x, this is a function of x y z. If I change my x y z, the value T, the function will going to change. But why it is a scalar field? Because temperature itself a scalar quantity, it should have a magnitude, there is nothing related to direction. So, that is why the temperature is an ideal example of a scalar field. In the similar way, we can have vector field. What is vector field? A function of a space whose value at each point is a vector quantity. Example: gravitational force, very common example. So, again I can have a coordinate system defining a space, say Cartesian coordinate system with x, y and z, and at any point I can have a gravitational force, and this should be a vector quantity because it should have a direction as well. So, it should be a function of x, y, z, but the only difference with the temperature is that it should have a value only, but here if I want to find out the gravitational force in this space, whatever the space I mentioned, that this should be a vector quantity, and that is why it becomes a vector field. So, scalar field and vector field are varying functions. In one case the function should be a scalar function, and in other case the function should be a vector function. Let us try to understand this in this very simple way. Well, then let us directly understand the details about the vectors, the properties about the vectors. Vector, already I defined that vector is something which should have a direction and magnitude. So, if I now represent these things in a space, then it should be like a arrow, where the length of this arrow is the magnitude and direction of this arrow gives the direction. These two quantity I am just supplying here, And now I define this quantity, the vector, like A. What is A? A should contain, this vector A should contain the magnitude of all these things, I write is magnitude, and also the direction, I write a direction here. Now this magnitude A, here A is the magnitude. And A defining the direction, and that should be a unit vector along the direction of the vector I defined. So it should be unit vector along the direction. Okay, fine. Now if I want to find out what is this unit vector from this expression, whatever the expression is written, I can simply write that unit vector is nothing, whatever the vector is given to me, then divided by the magnitude of that vector. So that simply gives me the unit vector. Now what is the magnitude of the unit vector itself? So the magnitude of the unit vector itself, if I want to find out the magnitude, then I want to make the magnitude for both the side of this equation and gives me unity, and that is quite obvious, because since it is a unit vector, it should have a magnitude, and this magnitude should be unit. Next very important thing, and that is component of components of the vector and basis. Very important term, basis. What do you mean by basis? That I like to explain here. So, what is component of the vector and what is basis? So I already mentioned that a vector one can define in coordinate system, and if this is a coordinate system, Cartesian coordinate system x y z, say x y z, I can define a vector like this. Now normally this is a 3-dimensional system, but there is a possibility that I can also imagine the abstract space where more dimensions are possible, still the vector is well defined there. So let us now restrict ourselves into the 3-dimension case. A vector is represented in this 3-dimension coordinate system simply by the component, with the combination of the component and basis. If I write it, it should be written in this way. A1, A2, A3, these are the components of the vector, and E1, E2, E3, these are the bases along these 3 directions x, y, z as per as this figure. So A1, A2, E3, as I mentioned, these are components. I can decompose a vector along this 3 direction, and if I do, then I should have the components in these 3 direction. We should call it as a projection. So these are the components, and these E1, E2, E3, these are the bases. These are the bases. Fine. Now if I want to find out the magnitude, the way we define that what should be the magnitude of this vector if it is given in this component form with basis, the magnitude should be simply the components sum of all the components square and root over of that. That should be the amount of the magnitude. Now, what are the properties of E1, E2, E3 basis? That is rather important here, and that property is very interesting. If we consider the coordinate system like this, this is a straightforward Cartesian coordinate system. If we use the straightforward Cartesian coordinate system, these bases should have certain relationship to follow, and that is EI dot EJ is equal to delta Ij. What is delta Ij? I will just discuss, but that means if I now write in a explicit way, it should be E1 Ijk can take the value 1 to 3. 1 to 3 means here x, y, z. So, E1 dot E1, that should be equal to E2 dot E2, that should be equal to E3 dot E3. These are the unit vectors. So, their magnitudes are 1 that I mentioned, that should be equal to 1, and E1 dot E2, apart from 1, if I now make a dot product with any other basis, E1 dot E3 or E2 dot E3, these are the possible 3 combination one can have, then that should be 0. So, all this equation you can write at a stage, at a simple equation using this delta function, that EI dot EJ is delta function. Now, this is true, this is not always true that all the bases should follow this, but this is true if the basis follows a property called orthonormal. They are orthogonal, that means they are perpendicular to each other, like the way we have here in Cartesian coordinate system. They are perpendicular to each other, that means this angle and these angle are 90 degree, and the unit vector that we have the unit vectors here E1, E2, and they have the value 1, that is why it is called unit vector. So, this is called the orthonormal basis. Orthonormal. So, orthonormal, this is the orthonormality condition. Normally, we use this orthonormal condition always, orthonormal basis always to to present a vector, because it has certain advantages, and we will discuss maybe these advantages. But you should know that there may be some bases which are not orthonormal, but in that case to represent a vector should be very complicated. So, better let us stick with this orthonormal basis, where the EI dot EJ delta Ij, this condition is always followed. Now, not only that, we should have another properties of this. We have the dot product of 1 and 2 and 3. Also, we should have a relationship with the cross product, and that relationship is called the cyclic relationship, and that relationship says that if I have EI and if I cross E2, then it should be E3. If I have E2 cross E3, it should be E1, and if I have E3 cross E1, it should be E2. So, they are following a cyclic rule, and that rule is like this. One, 2, 3. So, 1 cross 2 it will give you 3, 3 cross 1 it should give you 2, and 2 cross 3 it should give you 1. So, this is the cyclic rule. Okay. And also I mentioned that if these bases are forming a orthonormal basis, then if I want to find out any component, say ith component, if I want to find, then I just need to have E dot A. If I make a dot product with the entire vector with the respective basis, then whatever we have, that this component, and it is true only when these bases are orthonormal. If it is not orthonormal, then it will be very difficult to find this component. Okay. So, also now I like to mention that a given vector A can be decomposed in different bases. For example, here I am having the decomposition of A with one system where the unit vectors are EI, but the same vector can be decomposed in the other basis also. Let us consider this is a prime basis. So, obviously, there should be certain relationship between the E1 and E prime that we going to understand, but before that few more properties of the vector. These are the well known properties, but still I think I should mention. So, one is the vector addition. Vector addition. So, vector addition suggests that A plus B equal to C vector, and we can add this vector with certain laws that we know, that if this is my A vector and if this is my B vector, so I can have this rule. This is a well known rule. I am not going to explain this here. So, this should be my resultant vector C. Or I can have the A vector here, the triangle rule, and this is my B vector, and if I join from here to here, I will have my C vector. That is all. Apart from that, vectors are also following certain very trivial rules. For example, A plus B vector should be equal to B plus A vector. These are the vector addition. This looks quite simple, but it is not always. So, these are called the commutative property. Then also A plus B plus C, whatever the vector you will get, it should be A plus B plus C. You first add B C and then add with the vector A, you will get the same result if you add A B and then add C. So, this is called the associative. And if lambda is a scalar quantity, and then you can have lambda multiplied by 2 a vector A plus B, then you will get the same result if I have this is called distributive. Okay. So, finally, today I will like to just mention two very important vectors that we will discuss, that will be useful. One is called the position vector. So, if in a coordinate system like x, y, z Cartesian coordinate system, if I write any point at say P at x, y, z, this is defined with a vector called r, and this r vector is called the position vector, because any point here or here or here I can define a r vector that basically gives me the position of that particular point, and r vector is defined in this way: x I plus yj plus zk, where I, j, k are the unit vectors along x, y, z. Normally we write in I, j, k form. It can be also written E1, E2, E3, but normally we use for Cartesian coordinate system we use I, j, k. Well, another vector also important, and that is called the distance vector. A similar kind of vector, but it gives me the distance between 2 points. The same coordinate system, I have a coordinate system here, and suppose I have a point here P and Q, coordinate is x, y, z, say 1, 1, 1, x 1, y 1, z 1, and Q is x 2, y 2, z 2. Then the distance between these 2 points also give us a vector. So, first I need to know what is the position vector, say this is r 1, what is the position vector, this is r 2 for this point. So, what is the distance vector from here to here. So, this distance vector, if I define this distance vector as say big R, then big R should be equal to r 1 r 2 minus r 1, or in coordinate system it should be x 2 minus x 1 I plus y 2 minus y 1 j plus z 2 minus z 1 k. So, that should be the distance vector. So, with this note, today I do not have much time. So, with this note I would like to conclude today's class. In the next class we will learn more about the vector operations and the different aspects of vector. So, with that thank you for your attention and see you in the next class.